Good afternoon, everyone. This is Dr. Ahmed Fattah at KFUPM University in Saudi Arabia, and I'm presenting today the applicability of applying dry fibers to confine concrete circular stub columns. And this presentation is for the memory of Dr. Asad, that I have known him since 2007. He served as my co-advisor in my master's, and then he was a member in my committee for my PhD. So I always know Dr. Smiley as optimistic, full of positive energy, and smiling all of the time, so that his loss was a shock for me, and I'm 100% sure that it's the case for everybody who was in close contact with Dr. Smiley. So the presentation today is going to be divided into these segments. First, we'll just introduce the background about the problem, materials used. Then we'll talk about the setup, and then eventually we'll get to the results and conclusions. The idea started by Dr. Rashid and myself when we suggested replacing the steel ties with dry fibers in order to mitigate the corrosion impact, as well as get some improvement in terms of the strength. And we've used carbon and glass fiber yarns. And as you see here from the results, there was some improvements in it, but it was limited. And that is because of the stress concentrations that happen to be between the rebars and the rebars and the FRP or the fiber yarns, so that it was segmented, not circular, similar to the steel ties. So that we expanded the theory here, or the research, and then we took it as one step further, and we say, why not applying this as external device to confine concrete, to take advantage of the circular shape of the concrete, so that the FRP or the yarn is going to be oriented in a circular way. This method has several advantages over the traditional way of wrapping the concrete with sheets, because here we don't have to prepare the surface, and at the same time we're not facing any delamination problem, as well as we're not concerned about the gluing agent, since the fibers are going to be wrapped around the concrete multi-times or several times, so that it's going to confine more effectively. In addition, that it's going to be locally applied at different intervals among the column, or in the length of the column, so that it's going to be localized, and the column by itself might be engraved to host this fiber, and this fiber eventually can be protected by grouting or by plastering, so that we also mitigate the problem of the fire hazards. The material that we used here was glass fiber. The manufacturer was Taishan, and the tensile strength was about 2200 megapascal, and the tensile modulus was about 75 gigapascal. The variables that we used in this study was two things. First of all, or the first one was the lateral spacing. The second one was the thickness of the wires. And as you see from the specimen naming, we have two numbers. The first number reads the lateral spacing, being 1 is 40 millimeters up to G4, which is representing 10 millimeter spacing. The other number, which is followed by the dash, is how many wires are used, and we have also a range from 10 up to 40 wires. The following slide shows to you here the different setup of the specimen before rupture, and with different spacing and different number of wires. And as you see here, as it gets higher in number of wires and closed spaces, it becomes almost as sheet. And that is obvious on the specimen that is on the far right. The testing, we had two LVDTs attached to the concrete to capture the shortening, as well as two strain gauges oriented laterally, as you see from the image here, in order to capture the lateral expansion of the concrete, as well as we have the loading cell. We attach all of these to data loader and start gradually loading in order to capture the change in dimension and a change in loading. This is a figure. This is a video that shows the setup, and of course we added more fibers towards the top and bottom in order to push the failure to happen in the middle. As you see here, lots of crack developed, and then eventually we see rupture of the fiber bars in the middle, and that was confirmed by all of the specimen. All of them just experienced the same way as shown in the video. This is how the samples reflect the covers falling and the rupture of the FRP bundles. For the results, we arrange it in two different setups. The first one is to just capture the behavior while we are fixing the spacing. The other setup is where we are fixing the number of the wires, so that the first set is just representing having the same spacing. And as you can see here, as the fibers get more intense, more wires, the behavior of the concrete becomes similar to the concrete that is exposed to the sheet, FRP sheets, as you can see here from the gray curve, and that is very clear in here, whereas the one that has 10 wires didn't experience the same one as the gray. And for the lateral strain, the opposite, of course, happening, where we are having decrease in strain as the spacing get increased. Whereas for the axial strain and the axial stress, of course, the obvious notice that we have here is that increasing the number of wires would definitely increase the ultimate strength of the concrete. This observation was generalized for all of the cases, so that we can see here the behavior. Of course, after reaching the ultimate strength, the concrete experienced some softening happening towards the end of it. This was for the G2, which is the spacing, and then G3, which is the about 30 millimeter, which is 15 millimeter spacing, and then we have this one that is representing 10 millimeter spacing. And of course, we didn't get a chance to have the column with the high number of wires and close spacing, because it's not gonna be practical to be adjusted for the small scale columns. However, we can see the behavior here when it gets closely spaced. The behavior is almost similar to the concrete that is exposed to the sheets. Here is the other setup where we are having the number of the wires fixed and then the spacing vary. And here there is no surprises. We have a nice pattern that increasing the increasing the spacing will reduce the strength as traditionally known for the structural purpose of confinement. Here is the G20 and the 30, and when we compare this to the wrapping internally to replace the steel, we can see that there is huge improvement that happened to this externally applied confinement, so that we can get up to here for this case, for the The highest case was 58 megapascal compared to the 22 for the unconfined concrete, which is huge improvement in the performance of the concrete. The other setup, or the other set that we make comparison between the axial stress against the number of wires and the spacing. And as you can see here, the axial stress becomes more sensitive to the spacing as opposed to the number of wires. And when we did plot the same thing for the axial strain against the number of wires and spacing, we have noticed that the impact of the number of wires and spacing are equally applied on the axial strain. And that is, of course, due to the level of confinement. As we increase the confinement level by increasing the number of wires, we will have limited expansion in the concrete, which affect eventually the lateral strain. Then when it comes to the model proposed, we adopted the equation of equilibrium of at the level of the confinement between the lateral confinement and the stress developed in the FRP wires, and by equating here the forces in opposite direction and account for efficiency factor KE, which account for the discontinuity of the fibers that is not applied all over the cross section, which is going to be a factor of less than 1 or a fraction of 1. So the proposed also taking advantage of the behavior that we have seen. We took the bilinear model so that we have a model that is bilinear, started to have a linear model for just the behavior without having any confinement engagement, and after that, when the confined get engaged, the behavior change in the directionality of the column. And of course, we accounted also for that the efficiency of the lateral forces, lateral stresses, is about 0.5 multiplied by the efficiency factor multiplied by the ultimate strength of the FRP. Here also, we accounted that the FRP, the stress in the FRP is a function of the epsilon, the strain effective, and this strain effective, we account for the premature failure due to the curvature of the FRP to be 0.5 of the, or 50% of the ultimate strain of the FRP, whereas the ultimate strain for the concrete, we account to be 0.002 multiplied by 1 plus 3.5 multiplied by the ratio of the lateral efficient confinement divided by the concrete strength. Upon plotting those, we find that we have a good matching between the theory and the ultimate values of the, or the experimental values of the experiment, and we did not get a chance to capture the softening of the concrete. However, this can be easily adjusted. When we get to the conclusion, find out that using the glass fiber bundle of 30 wires increased the strength by 175% compared to the unconfined strength. Also using 30 wires of the glass fiber improved the ductility to 12 times greater than the unconfined strain value. Also, axial stress is dependent more on the confinement more than the number of wires, whereas the axial strain is impacted by both action, the spacing, and the number of wires. And then we adjusted, or we developed a bilinear model that can capture the critical points on the experimental case. By this, I finished my presentation. And if you do have any question, I'll be happy to answer them by addressing them to my email, which is shown in the last slide here. Thank you so much.